Do you think it's a fundamentally mathematical pursuit of trying to understand like the laws of this that govern our universe from a mathematical perspective? So almost like if it's AI, it's exploring the space of like theorems and those kinds
Hmm.
of things, or is there some other is there some other more computational ideas, more sort of empirical ideas?
They're both, I would say. It's really interesting to look out at the landscape of everything we call science today. So here you come now with this big new hammer. It says machine learning on it, and ask, where are there some nails that you can help with here that you can hammer? Ultimately, if machine learning gets to the point that it can do everything better than us, it will be able to help across the whole space of science. But maybe we can anchor it by starting a little bit right now, near term, and see how we kind of move forward. So like right now, first of all, you have a lot of big data science, right, where, for example, with telescopes, we are able to collect way more data every hour than a grad student can just pour over like in the old times, right?
Mm-hmm.
And machine learning is already being used very effectively, even at MIT, right, to find planets around other stars, to detect exciting new signatures of new particle physics in the sky, and to detect the ripples in the fabric of space-time that we call gravitational waves caused by enormous black holes crashing into each other halfway across our observable universe. Machine learning is running and ticking right now, doing all these things, and it's really helping all these experimental fields. There is a separate front of physics, computational physics, which is getting an enormous boost also. So we had to do all our computations by hand, right? People would have these giant books with tables of logarithms, and oh my god, it pains me to even think how long time it would have taken to do simple stuff. Then we started to get little calculators and computers that could do some basic math for us. Now what we're starting to see is kind of a shift from GoFi computational physics to neural network computational physics. What I mean by that is most computational physics would be done by humans programming in
Right.
the intelligence of how to do the computation into the
Mm-hmm.
computer. Just as when Garry Kasparov got his posterior kicked by IBM's Deep Blue in chess, humans had programmed in exactly how to
Yeah.
play chess. The
Yes.
intelligence came from the humans. It wasn't learned, right? Mu Zero can beat not only Kasparov in chess, but also Stockfish, which is the best sort of GoFi chess program,
Mm-hmm.
by learning. And we're seeing more of that now, that shift beginning to happen in physics. So let me give you an example. So lattice QCD is an area of physics whose goal is basically to take the periodic table and just compute the whole thing from first principles.
Mm-hmm.
This is not the search for a theory of everything. We already know the theory that's supposed to produce as output the
Mm-hmm.
periodic table, which atoms are stable, how heavy they are, all that good stuff. Their spectral lines. It's a theory, lattice QCD. You can put it on your T-shirt. Our colleague Frank Wilczek got the Nobel Prize for working on it. But the math is just too hard for us to solve.
Mm-hmm.
We have not been able to start with these equations and solve them to the extent that we can predict, oh yeah, and then there is carbon, and this is what the spectrum of the carbon atom looks like. But awesome people are building these supercomputer simulations where you just put in these equations and you make a big cubic lattice of space, or actually it's a very small lattice because you're going at the subatomic scale, down to the subatomic scale,
Mm-hmm.
and you try to solve this. But it's just so computationally expensive that we still haven't been able to calculate things as accurately as we measure them in many cases. And now machine learning is really revolutionizing this. So my colleague Fiona Shanahan at MIT, for example, she's been using this really cool machine learning technique called normalizing flows, where she's realized she can actually speed up the calculation dramatically by having the AI learn how to do things faster.
Mm.
Another area like this where we suck up an enormous amount of supercomputer time to do physics is black hole collisions. So now that we've done the sexy stuff of detecting a bunch of this
Mm-hmm.
with LIGO and other experiments, we want to be able to know what we're seeing
Mhm.
And so it's a very simple conceptual problem. It's the two-body problem. Newton solved it for classical gravity hundreds of years ago, but the two-body problem is still not fully solved
For black holes.
In Einstein's gravity, because they won't just orbit each other forever anymore. Two things: they give off gravitational waves, and eventually they crash into each other. And the game, what you want to do is you want to figure out, okay, what kind of wave comes out as a function of the masses of the two black holes, as a function of how they're spinning relative to each other, etc. And that is so hard. It can take months of supercomputer time on massive numbers of cores to do it. Wouldn't it be great if you can use machine learning to greatly speed that up, right? Now you can use the expensive old GoFi calculation as the truth, and then see if machine learning can figure out a smarter, faster way of getting the right answer. Yet another area like computational physics. These are probably the big three that suck up the most computer time: lattice QCD, black hole collisions, and cosmological simulations, where you take not a subatomic thing and try to figure out the mass of the proton, but you take something it's enormous and try to look at how all the galaxies get formed in there.
Oh, wow. Yeah.
There again, there are a lot of very cool ideas right now about how you can use machine learning to do this sort of stuff better. The difference between this and the big data is you kind of make the data yourself, right? So, and then finally, we're looking over the physics landscape and seeing what can we hammer with machine learning,
Yes.
right? So we talked about experimental data, big data, discovering cool stuff that we humans then look more closely at. Then we talked about taking the expensive computations we're doing now and figuring out how to do them much faster and better with AI.